Assalamualaikum warahmatullahi wabarakatuh. My name Muhammad IZUDDIN bin GHAZALEE. My ID number CE 180044. So I will talk about introduction. So we go to for our project background, which is manufacturing is defined as to make something from raw material by hand using machine, which is good through the use of tool, human labor, machinery, and mechanical process. So we built a biscuit factory, which is for making this conventional activity in many part of country. So major and minor ingredient used during manufacturing of biscuit play an important role, and the chemistry behind them must be well understood by biscuit manufacturer to maintain quality and to avoid batch variation. So in our biscuit manufacture, which is we focus three section only, which is mixing, baking, and packaging, because this part very particular to to design the circuit, the one line diagram for electrical power system. So and then we go through for technical problem, which is power system planning is an important aspect of the planning and design of an electrical power system, which is we need to understanding the specific situation and environment surrounding the project to carry out the planning work prior to the implementation of the power electrical in this project. So what we need power source planning entail. In preliminary stage for this project, we need to design and study about the distribution of power grid around this project. So we need to study the power output in the order to carry out the overall analysis of electrical power project and provide scientific basic from electrical power system construction, which is we need to calculate like total power demand, total load, and others. And furthermore, usually the balance of electrical power and energy has certain restriction on the planning and design of the power system. First of all, after the prediction about the power load and getting an overall understanding of the output data, we as our engineer, we need to design equilibrium calculation about electric power and energy of the power source, and carry out detailed analysis and statistics of the result to facilitate the layout of the electric power project and design of its scale. And what's important, the electrical calculation, which is electrical power system planning and design. In the design electrical power engineering, electrical calculation generally include load flow calculation, stability calculation, reactive conversion calculation. So which load flow calculation refer to the calculation basic of the power and voltage and power network.
Assalamualaikum warahmatullahi wabarakatuh. My name is AHMAD ZARKHONI bin AZIZ. My metric number is DE180173. So I will explain the calculation in Microsoft Excel for this project. So basically, this is the load description for this project, or for this sweet biscuit factory, that has been given in this instruction, which is at least 24 number of load. So we have divided the load given in 3 feeders, which is A for mixing, B for baking, and C for packaging. So each of the load have their own duty, which is S for standby, C for continuous, and I for intermittent. And the calculation will be use this formula. So for standby, which is fire water pump, for example, in kilowatt, we have to use the value absolute load 75 divided with 88 from efficiency over 100. So we will get 85.23. For kVAR, we need to use this value 85.23 square root 1 over 0.74 from cos power 2 theta minus 1. So we get 50.52. And for kVA, use Q4 also 85.23 over 0.86 from power factor times with 88 over 100. So we get 112.62. So for continuous and intermittent also use the same formula as standby. So this is the total amount of each of the continuous for kilowatt, kVAR, and kVA for continuous, intermittent, and standby. So this is the operating load. So operating load will use this formula, which is 0.5 times with N40. N40 is 290.91, which is from intermittent kilowatt, plus K40. K40 is kilowatt continuous. So we will get this operating load in kilowatt. For peak load, we use this formula, and for design load, we use this formula. And for how to get the overall power factor, we need to add, which is first we need to add D40, which is this value operating load plus peak load plus design load over with operating load in kVA plus peak load plus design load. So we will get 0.75. And this is the value for line current, which is 18149.5. So that is for estimated power demand. For maximum power demand, how to calculate the input power? So we use I4 over H4. I4 is from output power over with K, 85.23 over 0.76. So we will get 112.62. So 412 will be in total kVA. So for input power, we'll use all the same formula, and we can see from input power we will get the total kVA. So the total amount of kVA for all of the load is 6,032.21 kVA.
Assalamualaikum. My name Ibrahim Arif. So today I will explain a little bit about the Excel, which is the apparent power demands. So we have three feeder, which is feeder A mixing, feeder B baking, and feeder C packaging. So for feeder A, we have 12 load. Feeder B we have 11 load, and feeder C also have 11 load. So for the load, we arrange the load based on the voltage and the load that use motor or not. So for the example, number 1 until number 7, the load do not use the motor, but number 8 until 12 use the motor. So for the kVA, we get from the maximum power demand, which is the total kVA. The Ku is we are refer to the slide. Then after we got two value, we can calculate the value of the kVA after we multiply S and Ku. Value of KS1 also we refer to the slide. As we can see, the KS1 of the load that use motor is 0.8. So from that we can get the value of the SDB, and then this is the value referred to the slide. After we got this, we can get the value of SPDB, and then we refer to the slide again for the KS3, and then lastly we can get the value of the SMGDB. Okay, after we finish this Excel for apparent power demand, we can create a circuit on the ETAP based on this, which is this is for the upper transformer, main transformer, and this, and then this for feeder 1, volt kVA for feeder 1, feeder A, kVA for feeder B, and kVA for feeder C. Okay, then we calculate the transformer, which is the distribution transformer. We get the apparent power demand, which is 2596.46, and then this is 65% from kVA. Then we got the transformer rating selection, which is 5000. So for the main transformer, the construction type is oil field. So the other three transformer is same type, which is oil field and dry type transformer. For the first transformer for feeder 1, with rating 2015, transformer 2 1K, and transformer 3 2K. So this is we refer to the slide. The transformer rating value of primary, which is 20 to 24, secondary 3 to 12, the construction type oil field, and impedance range 5 until 50%. So this all value we will put on the parameter on the ETAPs. Okay, so that's all from me. Thank you.
Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Syed Amiruddin Hilmi bin Syed Muhammad ALBAKIR. My matric number DE180111. Okay, for the voltage drop happen in this industry known as amount of energy given by a voltage source as it travels through passive component in an electrical circuit. Voltage drop across the source internal resistance, conductors, contacts, and connection are undesirable provided energy is waste. Voltage drops across load and other active
circuit component and desire since the provide energy is put to good use in the process. With this, voltage is a measure of energy per change. An electric heater may be powered by wires that have an overall circuit resistance of 10%, and the wires that feed it may have a resistance of little over 2% of that. This indicates that around 2% of the power provided is waste in the wire itself. Electrical and electronic device may malfunction of or be damaged if the voltage drop is excessive. Okay, this is for the transformer for voltage drop. Transformer size 6000 and 3000, and transformer secondary voltage V2 22 impedance of Z 5.5%, and for voltage drop for transformer 10%. Okay. For the motor power 200 kilowatt, and motor horsepower 268.1, voltage to 22, power factor 0.8, and efficiency 75%, and for the motor 333 and 0.33. Okay, for the motor code selection, motor code D, motor full load current 6.56, load rotor current multiplier 4.1, load rotor current multiplier max 4.5, and load rotor current L1 min 26.9, and load rotor current for L1 max 29.52, and for voltage drop, motor in rush kilowatt at starting 7381.11, and full load current of transformer 165.34, and short circuit current at secondary transformer 3006.13, and max for of secondary transformer 1145.45, and voltage drop at secondary transformer due to motor in rush is 6.44%. Okay, next I will explain about the cable sizing for this industry. For first, maximum load per feeder kVA for cable sizing 2569.46. For current per feeder A is 1286.13, and for insulation material is final temperature SLPE 250. For constant per cable 143.08, and for shearing time for time cycle is 0.3, and sizing of the cable 4.92 mm. And so for next, for cable sizing 1214 is current 551.56, and final temperature also. And for SLPE 250, and for the constant per cable 143.08, and fault carrying 0.2, and size 1.72. And for cable sizing, maximum load per feeder 48.5.04 is current per feeder 375.01, and for insulation material is international temperature SLPE is 90, and constant cable also same, and fault carry time 0.2, and size the cable 1.17. And last, for cable sizing, maximum load per feeder is 1155.7 for current per feeder 359.55, and the insulation material is initial temperature and SLPE 90, and also constant per cable 143.08 and fault carrying time for time cycle is 0.2, and size of the cable is 1.12. Okay, that's all. Thank you.
Assalamualaikum and hi, my name is AHMAD FIRDAUS by Muhammad ZEINI DE180101. So for today, I will explain about my simulation on ETAP. First of all, our factory is a biscuit factory, sweet biscuit factory. In this factory, it is divided into three departments. First, feeder 1 is mixing, feeder 2 is baking, and feeder 3 is packaging. Our system is provided with a transformer and standby transformer. Standby transformer is prepped for if any fault or damage occur at normal transformer, so we can use the standby transformer. Our system also provided with a protective device such as circuit breaker and relay. Relay is used to summon any circuit breaker if there is a fault occur at certain place. Okay. So our system is supplied by TMB, which is 6.6 kilovolt. Then each feeder will receive 6.6 kilovolt. Then it will be stepped down into 3.3 kilovolt and 415 volt according to the loads. Okay. For the cable use, first we must put the length for the system and ampere current that received at the cable. After that, we choose standard, and type of the cable is underground duct. So our required cable is for the system is 300, 191.1 and 2. So the optimal size is 300, 205 ampacity with also with 0.02. Okay. For the circuit breaker, we need to choose from the library the maximum kilovolt based on the load that we want to use. Then we can get the maximum volt and its continuous ampere based on the library. For the relay, the primary ampere is 1486 and all the secondary ampere is 1. So for the output, for example, this relay at load 1, if any fault occur, it will summon relays. It will switch on circuit breaker 29, circuit breaker 14, and circuit breaker 15. Okay. Okay. For the power flow analysis, from the TMB, we will receive 100% of voltage. Then when it reach to SMGDB, there is voltage drop 99.9%. And for the each feeder, the lowest is 95.5%. However, it is considered still in good condition because it is not less than 10% of voltage drop. Okay. Next, we go to the fault analysis. Fault analysis is divided into four, which is load, SPDB, SMGDB, and TMB. Okay, first we go to the load. For the load, if fault is occur here, circuit breaker will open here and here and here. So when fault occur at this load, all system at such as this area, feeder 2 and feeder 3 will still continue. Okay, next we go to the SPDB. So when fault happen here, circuit breaker will switch on at CB7. So all the system in feeder 1 will shut down. However, feeder 2 and feeder 3 will still continue. So this will not affect them. Okay, next we go to the SMGDB. If we apply for SMGDB, first it will shut down feeder 1, feeder 3 and feeder 2. So and it also will shut down at main supply. So when fault occur at SMGDB, all the system will be shut down. Okay, lastly, if fault occur at TMB main supply, circuit breaker will switch on at feeder 1, feeder 3, feeder 2, and also at the circuit breaker at the TMB. So all the system will shut down and it need for a maintenance. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. So my name is HAKIM BAHRI. So I present about chapter 3. So this is Excel for the outcomes of the load demand estimation. So in this part we will go over the features from the Microsoft Excel tool and how to estimate the overall load demand of an industrial power network to meet the project's goal. Okay. So here I present there is a estimated power demand right here. Okay. As we will use an industrial power network to display the mains, distribution transformers, cables, incoming and outgoing feed lines, and the motor control center MCC. So as example in this project, to identify and estimate the overall load demand, so the expected power consumption of the industrial power network is shown in the following Excel right here. Shows that the industrial power network requires 13,045.88 kilovolt. Okay. For the total apparent power with a minimum supply voltage of 11 kilovolt. Okay. So proceed with this apparent power demand and appropriate utilization factor, that is KU, and a diversity factor, that is KS, for each load. It must be determined based on the number of hours per day that the load is in operation. So heavy machinery with a high frequency of operation would be benefit from an appropriate utilization factor between right here 1.0 and 0.8. So for a lot less load, a utilization factor of 0.2 might be more appropriate. Okay, so for KS1 and 2 and 3 may now be used to identify the rating diversity factor, the SKS, for each load separately. So KS1 rated diversity factor is 1.0 based on the utilization factor for each heavy machinery given in this Excel. So the rating variety factor of 0.2 was used for the less heavy loads. So for KS2, the rated diversity factor is determined by comparing the rated diversity factor stated in KS1 to the total specified loads, where 0.7 is the appropriate rated diversity factor. So appropriate rated diversity factor is 0.9 that is found for the total load in KS3 by taking into account the selected these rated diversity factors indicated in KS2. So the value of the sub main general distribution board is SMGDB will be 3281.35 kilovolt. So if KS3 is multiplied by the total of the values mentioned in the SPDB. Okay, so proceed with this. Okay, so the total maximum demand of industrial loading must be less than or equal to 65% of the size of full load transformer, since we see 6300 kV is greater than 65% of the entire maximum demand of 6229.13 kV. So the transformer rating for the discrete factory is 6300 kV as stated in the table. Okay, it will alert the user if the transformer rating selected is lower than predicted maximum demand and encourage the user to choose a higher transformer rating. Okay, like this. Okay, so I proceed with the 3.2 right here. So this is 3.2 for the outcomes of industrial network design. So this is a one line diagram. Okay, so as may be seen in the picture right here, a three-phase system is balanced. So positive sequence diagram is another name for this figure. So positive, negative and zero sequence networks are shown in 3 unit design. In the short circuit, 3 distinct impedance diagrams are utilized to study asymmetrical faults. So from the one line diagram, it can improve in troubleshooting timing and makes troubleshooting more efficient. So using this single line diagram that is accurate as possible can help to guarantee the safety of focus, complies with all relevant laws and regulation as well as industry standard. Okay, so I proceed simulation result and discussion. So this is our simulation from the ETAPS. So there is here TMB fault. So circuit breaker CB52 will be triggered if a fault occurs in the LV bus bar. So protecting the transformer and other system, other circuit breakers CB17 through CB20 are then turned on one at a time to safeguard the system's others components. The CBs at the system upper and lower ends were open. So a fault current of 59.241 kA has been detected. Okay, this is for the fault load for SPDB F1 and for SMGDB bus bar. So when a problem develops with the SMGDB bus bar, the 11 kV incoming circuit breaker is open. So after that, the transformer circuit breaker are used to separate the transformer from the rest of the electrical system. Okay. So lastly, for the environment and sustainability, so what is a proper solution? The facilities, operation, goods and services have an environmental effect if they alter the environment in any way, so whether negatively or positively. So an increase in the use of inefficient energy from a sweet cookie business that use a lot of electrical device may hurt the environment and contribute significantly the global warming. So the environment in sweet biscuit factories is the noise generated by equipment such as vacuum, dryer pumps and vibrating presses. That is example of the thread. So the power factor is the most critical component to take into account while designing an industrial system. So to avoid penalties, each user must keep their power factor over 65%. So the power factor of a grid or other system will reduce the power factor of the grid when it's lower. So power losses and decreases efficiency may be caused by a power factor. So by reduce fuel power production may preserve our planet by lowering our energy usage. In addition, industrial waste must be controlled and treated or filtered in some manner. Okay, that's all from me. Thank you.
Last but not least, we need to conclusion for this project. In conclusion, the planning and design of electric power system is critical to design of electric power engineering and serve as a solid assurance of the entire electrical power system normal operation. As a result, our company must be prioritize the planning and the design of electric power system, which is we need to perform in early stage electric engineering planning and develop scientific or reasonable planning and design for the electric power system. In addition, we must make a point, collect experience and lesson from the this project to order continuously improve the quality of level electrical power system planning and design. And then as well as we need to promote the long-term development of electric power system planning and design of electric power engineering. As time pass and syllabus improve, we must continue to innovate the planning design of electric power system that we will be able to adapt power system to the changing demand of for our effort to foster the electric power industry strong and long-term development. So the weakness of the purpose design, which is the planning of electric power system, is complicated for our project to be run through the whole electric power engineering system and involve a broad scope and many influence factor. In terms of time, there are short term, medium term and long term to planning and design of electric power engineering system. So the major content of planning and design the electric power are generation, expansion, planning and output. And then the balance of power energy volume, system access plan and electric relay calculation. That's all.